Okay, so for today, we actually ended up not getting through the very last set of examples in second hour. So I'll probably kind of plan on that for today anyway, just finish that up tomorrow. But chapter 6, I did say when we started chapter 6, is on inverse functions and then also radical functions, because radical functions are are the inverse of a type of function we've studied already. So 6.1 was just working with how to combine functions, because we'll use that throughout this chapter and throughout future chapters. But then today we really review, I guess, from Algebra 1 what the inverse of a function or relation is and how to find the inverse. So there is a main idea behind an inverse that you need to understand. So if you're asked to find an inverse, the main relationship between a relation or function and its inverse, we'll be talking about that first. So we are finding inverses of just relations, so sets of ordered pairs, and then of actual functions where they're given as an equation. And I have at the top, just for you to remember or to recall, that a relation is defined as a set of ordered pairs. So it's a relationship between x and y. And then the inverse relation is the set of ordered pairs obtained by exchanging the coordinates of each ordered pair. So the big idea behind inverses is that the x and the y values switch. This describes it as the domain and the range switching. So the domain, the x values of the relation become the range or the y values of the inverse, and then vice versa. The range of the relation, the y values of the relation become the x values or the domain of the inverse. So that's what's explained in this box here. That two relations are inverse relations if and only if whenever one relation contains the element AB, so the x coordinate is A, y coordinate is B, then the other relation would contain the element BA, so now x would be B and y would be A. So they are just switching the x and the y coordinates. That's the big idea behind inverses, domain and range, x's and y's are switched. So that's also laid out in this example. So I'm just going to highlight this so you can more visually see it. But here, the relation A and the relation B are inverses. And you can see that the three x values in the ordered pairs for relation A are now the y values in the relation B. And then the y values in relation A are now the x values in relation B. And so the same x and y coordinate, they're still paired together. They just have switched places. So as long as you have that understanding of what an inverse is, that x's and y's switch, that'll definitely help in knowing how to find an inverse. You have to know the x's and y's switch. So in example 1, this is just finding the inverse of a relation. So it gives us a relation, and this relation, it tells us, represents the coordinates of the vertices of a right triangle, and it says find the inverse of this relation and then describe the graph of the inverse. So what I'm actually going to do first, this is kind of thinking ahead, because to describe the graph of the inverse, I also want to graph the original relation. So I'm going to graph these three ordered pairs first, and I know that they create a right triangle, so after I graph them, I'll draw the right triangle in. So I'm just going to plot these first on the grid that we have. So -8, -3, -8, -6, and then -3, -6. So this is the right triangle of the original relation. And then now I'll actually go back and find the inverse. We'll graph the inverse and then describe the relationship between the two graphs. So I will say this though as well, and this is going to apply to the functions we work with later. For this particular problem, if the original relation is a right triangle, the inverse will also be a right triangle. So if your original function, say, is a line, the inverse will also be a line. So the type of graph that you get doesn't change between a relation and its inverse. But what will happen, it'll be a reflection, which we'll see and we'll talk about. So the actual inverse of this relation is still a set of 3 ordered pairs, but for each of the ordered pairs, the x and the y coordinates just switch. So the in the original relation, the first ordered pair is -8, -3, so it'll now be -3, -8. Second ordered pair was -8, -6, it'll now be -6, -8. And then the last ordered pair was -3, -6, and now it's -6, -3. You should write it as a set still in the braces. If you left them off, say on a quiz, I wouldn't mark off. I'd probably just write them in. Okay, so I hate to say anything in math is easy because that's kind of up to you, but personally you're switching x and y coordinates. It's not hard to do that, but you have to understand that that's what you're supposed to do. So that's where understanding what an inverse is important. Otherwise, you don't know that you're just supposed to switch them. So then now I'm going to plot these 3 ordered pairs on the graph. And again, they still will create a right triangle. It just obviously won't be in the exact same place. So we have -3, -8, -6, -8, and then -6, -3. And if I connect those, like I said, I can still see it's a right triangle, not in the same place. But we're going to talk about what relationship those 2 graphs have with each other. And you might remember this from Algebra 1 anyway. So when a relation or 2 relations are inverses, their graphs are a reflection over a specific line. They're a reflection over the line y equals x. And I'm going to write that out here, but I just want to show you on the graph, if you graphed the line y equals x, so this line has a slope of 1 because it's 1x, and then a y-intercept or a b of 0 because it's like 1x plus 0. So to picture the line, it would be starting at the origin and then you're going up 1 over 1 to draw your line. So an easy way to kind of sketch it in, it's a line that would go through the lower left and upper right corners of your coordinate plane. So I'm just going to dash that line in so you can kind of see that, and it might be more difficult to see with this because of the triangles, but hopefully you can kind of see then if you look, and you might, tilt your paper to see it a little better, but if you actually looked along that line, hopefully then you can see how that reflection is happening. And the reason that 2 inverse relations are reflected over this line is because you're just changing your x and y coordinates, so it's reflecting over the line where x and y are actually equal to each other. So this statement that I'm going to write here is true for any relation and its inverse. I'm going to say the inverse relation is a reflection of the original relation over the line y equals x. Like I said, that's true for anything. So even the examples we're going to be doing in a little bit, where you're actually finding an inverse function and graphing the original function and its inverse, this should still be true. The inverse function is a reflection of the original function over the line y equals x. So use that as kind of a check if you're graphing a relation or a function and it's inverse and it doesn't appear that they're reflected over this line, something is wrong. And it could be just your graph that's wrong, or maybe you found the inverse incorrectly too. It's kind of a check. Okay, so questions so far just on what the idea of an inverse is or the graphical relationship. So we'll get into the functions next. Okay, so then, so getting into the functions, so just as with inverse relations, ordered pairs of inverse functions are also related in that same way. X's and Y's are switched, domain and range are switched. What I want you to note on this front page before we look onto the back is the notation for an inverse function. So if you have a function f of x, this is how you write the inverse. So it looks like f to the negative first power, and then of x, that is how you write it. But that negative 1 is not an exponent, it means the inverse. So you would read this as f of x inverse, or you could say f inverse of x. But the main thing is you need to know if you see that notation, that it means the inverse function. If you are finding an inverse function, you should be using this notation in your answer to represent the inverse function. So you want to know what that means. And then what this properties of inverses box explains is basically what the inverse relations box above explains. It just shows it with function notation. So I'm just going to focus on this first line here. It just says if f and then f inverse are inverses, f of a equals b. So that's saying for the original function f, the x value is a, the y value is b. And that's if and only if for the inverse function, the x value is now b and the y value is a. So it's just showing again the x's and y's have switched. It's that same relationship. This just gives a more specific example with actual numbers there. So then moving ahead here, before we get into example 2, because what you will be doing is not only finding an inverse function from an equation, but then also graphing the function and the inverse. And I want you to be able to understand if the inverse of a function is also a function. So you might remember, and it does say up here, I'm looking at the second sentence. So, well, I guess I'll start from the beginning. It says when the inverse of a function is also a function, the original function is 1 to 1. And it says recall that the vertical line test can be used to determine whether a relation is a function. So the vertical line test, again, you talked about that in Algebra 1. We reviewed it earlier this year. So if you have a graph of a relation, you would say, okay, if I draw vertical lines, as long as any vertical line only crosses through the graph one time, it's a function. So both of these are functions. They would both pass the vertical line test. There is also a horizontal line test, and the horizontal line test can be used to determine if the inverse of that function is a function. So just because something is a function doesn't mean its inverse will also be a function. So horizontal line test, just like the vertical line test, you would say, okay, I'm going to draw horizontal lines through my graph. And as long as every horizontal line only crosses through one time, then that means the inverse is a function. If it crosses through more than once, the inverse is not a function. So it is explained below for both of these. So for f of x here, if you drew in any horizontal line, it's only going to pass through one point. So therefore, the inverse of this graph, f of x, would also be a function. But for that second graph, g of x, notice the dashed horizontal line they already have there for you. That horizontal line passes through 4 different points. So then, because it passes through more than once, even though g of x is a function, the inverse of g of x is not a function. So why I'm covering that with you, when you are actually finding the inverse of a function, if the inverse is also a function, you should be using the function inverse notation in your answer. If the inverse is not a function, you should not be using the function notation for the inverse. So we have 2 examples to look at, and I'll explain more as we go through both of them. But that's why I'm pointing out and stressing that horizontal line test, so you understand if the inverse is going to be a function. So under example 2, we have one example on this page and then another example on the next. So we're doing a couple of different things, finding the inverse of the function and then also graphing the function and its inverse. What I'm actually going to do first is I'm going to graph the original function first, because then I want us to look at the graph to see will the inverse actually be a function. So This function that we have in part A is a linear function, and I know that because it has a variable x, and the x is to the first power. And if it's linear, I should be able to write it in the form y equals mx plus b. So I'm going to rewrite this so that it's in that form. Because I have x minus 3 all over 5, I can rewrite that so that it's x over 5 minus 3 over 5. So I can split it into two fractions. And then if this is even more helpful for you, x over 5, because there is a 1 in front of that x, is the same as 1/5 x, and then minus 3/5. So here you can actually see the mx plus b, if that's more helpful for you to look at. So I can see that my y-intercept, the b, is negative 3/5, which since I'm going to be plotting that on the y-axis, I'm going to write it as a decimal. It's negative 0.6. And then the slope m is 1/5. So I'm going to graph this first. So on the y-axis, again, I need to put my y-intercept at negative 0.6, so about negative 1/2. And then I can use my slope, my rise over run, to go up 1 over 5 to the right. And I know I didn't have rulers for you, so just do your best to draw your line in. I'm just making more points, so it's easier to draw a straight line. And I'm going to write by this here. This is my original function, f of x. And again, it's a line. So when you actually find the inverse and graph it, again, your inverse should not be a different type of graph. Your inverse should also be a line. So if you're getting something crazy and it's not a line, it's not right. But looking at this graph, would you say that it passes the horizontal line test? That if I draw horizontal lines, they'll only go through it one time? I see some yeses. So this does, I'm just going to make a note, it does pass the, and I'm going to abbreviate it. It's up to you on your notes how you want to write it. Horizontal line test, I'm just putting HLT. But if you're going to look back at your notes and not know what HLT means, I would write horizontal line test on yours. But it does pass the horizontal line test, and this means the inverse is a function. So when I go through my steps to find the inverse, in my answer, I should be writing it as a function. I should be using the f inverse of x, the function notation. If it were to not be a function, in the very last step, I'll show you what I mean. You would not use this notation because it's not a function. Okay, so that's just graphing the original, applying the horizontal line test. So now I'm actually going to find the inverse. So I'm just going to rewrite, because I wrote some stuff up here. I'm just going to rewrite the original function the way it was given in the problem. And there are 4 steps to finding the inverse of a function. So if it's given as an equation, there's 4 steps to find the inverse. And again, maybe this will seem familiar from Algebra 1 because it is a review. But the first step is to replace the function notation f of x with the variable y. So we know they mean the same thing. F of x is just the function notation. So you're putting y in place of the f of x, or g of x, whatever is there. And then your second step, so this is now where the inverse part comes in. Inverses, x's and y's are switched. So you then switch the variables x and y. Everything else stays where it is. So rather than having y equals x minus 3 over 5, I now have x equals y minus 3 all over 5. And then once you've switched x and y, then you solve the equation you have now for y. So you put y in a different spot. You now want to get that y by itself. So looking at the equation that we have here, what would we have to do first to get the y by itself? Okay. Yep. Cancel out that denominator on the right, so I would have 5x equals y minus 3. And then last step to get y alone, add 3. And then just remember, only combine like terms, so 5x plus 3 stays 5x plus 3. It's not 8x, and that equals y. Okay, so this is the inverse, but now because we said the inverse is a function, the last step then is to replace the y with the inverse notation, so the f inverse of x notation. And I'm going to switch it around too, so it's f inverse of x equals 5x plus 3. Okay, so if we had determined the inverse was not a function, I would have left the y there. That's good. Okay, so we're still going to graph this because it did ask us to graph both in the directions, but are there questions on how I found the inverse function? And regardless of what function you start with, those 4 steps are always the same. Okay, so then to graph this, like I said, it's also a line. So this one has a y-intercept of 3 and a slope of 5, or 5 over 1. So on my graph, on the y-axis, I should put a point at 3. And then my rise over run is 5 over 1. So up 5, right 1. Or down 5, left 1. And again, sometimes it's hard to tell, but you should kind of be able to tell if you kind of tilted your paper so you're looking at where the line y equals x would be, again, from that lower left to top right corner. You should picture, okay, if I drew a line in there, do these appear to be reflected over that line? Because that's a check to see if, the inverses would be graphed correctly, if it really seems like the correct inverse. Okay, questions? Okay. So then example B is a different type of function. So I want to go through this one with you as well. We have f of x equals 3x squared. So first of all, it's not linear because it has an x squared. What type of function has an x squared? Ethan, what did you say? Yeah, graph is a parabola. So what type of function has a parabola? Quadratic, yes. Okay, it's a quadratic function. Graph will be a parabola. And just like we did with the last one, I want to graph this first before we find the inverse. How did we graph parabolas in chapter 4? Okay, I hear axis of symmetry. So we made a table. I'm not asking you in this one problem to go into as much detail as we went into in chapter 4. You just need a quick sketch of what this looks like. But if you remember, we found the axis of symmetry, which helped us find the vertex. And then once you had the vertex, you could then choose points on either side so that you had enough points to draw a parabola in. So how did we find the axis of symmetry? X equals negative b over 2a. So for this quadratic function, what is the b value? 0. So it'd be the opposite of 0 over 2 times 3, but 0 over anything is just 0. So your vertex will occur when the x is 0. And then I'm just asking you here, you at least need 3 points to be able to sketch this in. So like I said, you don't need to have 5 for this. So I'm just going to do 1 point on either side. Oops, negative 1 and positive 1. and then substitute those in to get the y values. So I'm going to put 0 in first. If x is 0, 0 squared times 3 is still 0. And then positive and negative 1 should give you the same y value. Remember, when you substitute either of them in, you have to square the x first and then multiply by 3. So 1 squared is 1, multiplied by 3 is 3. And negative 1 would get you the same y value. Okay, so I can plot those 3 points. If you wanted to include more, you're welcome to, but for our purposes here, we're focusing more on the inverse side of things versus graphing this fabulous parabola. We've done that already. So as long as there's a quick sketch, it's fine. Okay, and then I'm going to find the inverse function. So I'm just going to rewrite f of x equals 3x squared. So following the exact same steps, even though we have a different type of function. Actually, before we find this though, does our graph pass the horizontal line test? No. If I draw a horizontal line through this, it's going to hit twice. So this does not pass the horizontal line test, and that means the inverse is not a function. So that means that step 4 that we had in the last process of writing the function inverse notation in our answer, you don't need to do that here. You just leave it as y because it's not actually a function. So here's our original function though. What was our first step to find the inverse? Yeah, so we have y equals 3x squared. Second step, switch x and y, and everything else stays where it is. So it's x equals 3y squared. So the 3 and the exponent of 2 stay exactly where they are. And then solve for y. So what do you do first here to solve for y? Before we take the square root, divide by 3. Divide by 3 and then take the square root. And when you have x divided by 3, you can leave that as x divided by 3. You could write it as 1/3 x. That's equal to y squared. Take the square root of each side. So we'll have y equals, what do you need to remember with taking square roots? Yep, plus or minus. That still applies here. And then we do not do the fourth step of writing f inverse of x because this is not a function. So this would be our inverse. So you leave it as y. So then to graph this, and I'll explain where the plus or minus come in on the graph. To graph this, we are also going to use a table, but we don't have to completely make a new table because we know inverses, x's and y's switch. We already have a table for the original, so all you have to do for your table here is switch your x and y columns. Okay, so here the x column was -1, 0, +1, that's now the y column. The y column was 3, 0, 3, that's now the x column. Okay, so you're just using that table then to graph this one. And I'm going to plot these 3 ordered pairs now. So 3, 1, 0, 0, 3, -1. And you still have a parabola, but it opens sideways. And again, if you kind of tilted your paper, you could hopefully see if you drew the line y equals x in there, that it would be a reflection over that line. So I'll quickly explain this because square root functions are part of this chapter. They are radical functions. So because a sideways parabola is not a function, if I just had the positive square root would be the top part of that parabola. So starting at 0, 0 and going up. And then the negative square root is the bottom part of that parabola. So separately, the positive square root and the negative square root are functions. together as one, sideways parabola is not a function, but it is the inverse. Questions on that? Okay.